When it comes to space exploration, some missions are measured by their data, others by their daring. But the Cassini mission to Saturn was something more. It was history unfolding in real time. 4 spacecraft had visited Saturn before, but none stayed long enough to truly know it. Cassini changed that. It was the first to orbit the gas giant, to study it season after season, and to watch its moons not as passing objects, but as evolving worlds. What we uncovered was not just scientific, it was poetic. Cassini became our silent witness in the cold outer solar system, turning Saturn from a distant icon into a living, breathing system. The mission revealed over a dozen new moons, captured hundreds of thousands of images, and returned measurements that rewrote textbooks. It was the foundation for thousands of scientific studies, and it inspired an entire generation of explorers. But perhaps the greatest truth is this: we were lucky. Lucky to have the timing, the technology, and the teamwork to make it happen. Lucky to see Saturn in such intimate detail, and lucky that Cassini, in its final moments, chose to fall, giving everything it had, so that we might understand just a little more about the universe we call home. Cassini's voyage to Saturn was never going to be easy. Reaching a world nearly 1.5 billion kilometers from Earth is not something that can be done by simply pointing and firing a rocket. Saturn lies far beyond the warm reach of the Sun, across a sea of gravitational currents that constantly pull, bend, and resist. Sending a spacecraft to orbit such a distant world required one of the most precisely calculated journeys in the history of space exploration, a cosmic slingshot that would take nearly 7 years to complete. Launched in October of 1997 from Cape Canaveral, Cassini-Huygens did not fly straight to Saturn. That would have required far more energy than any available rocket could provide. Instead, it followed a looping path around the inner solar system, using the gravity of nearby planets as stepping stones. This technique, called gravity assist, is like stealing momentum from a planet's motion. With every pass, Cassini gained speed, falling toward a world and then being flung outward like a stone from a sling. Cassini's first assist came from Venus, where it passed twice in close succession. These encounters bent its path and boosted its velocity. It then returned to Earth in the summer of the year 2000, flying just 1,100 kilometers above the planet's surface. That flyby was both critical and tense. Not only did it provide the final push Cassini needed, but it also brought a spacecraft carrying 33 kilograms of radioactive plutonium uncomfortably close to Earth. If the trajectory had been off, the consequences could have been serious. From Earth, Cassini raced outward toward Jupiter. That final encounter, in December of the year 2000, gave it the energy needed to escape the pull of the Sun and set course for Saturn. It is remarkable to think that this entire chain of events, this elegant sequence of planetary assists, was only possible because of a rare alignment that occurs once every 6 centuries. Miss the window, and the opportunity would not return in any living scientist's lifetime. Timing was everything. and the team nailed it. During its cruise phase through the outer solar system, Cassini remained far from idle. As it approached Jupiter, the spacecraft conducted a detailed flyby, taking stunning images of the gas giant and helping test its instruments. It also provided crucial data on Jupiter's atmosphere, magnetosphere, and moon system. This not only proved that the instruments were working, but also gave scientists a taste of what was to come. If Cassini could deliver this much insight at a distance, what could it uncover once it was orbiting Saturn? What truly powered Cassini through this vast expanse was not fuel, but radioactive decay. Solar panels would not have worked that far from the sun. Instead, Cassini relied on 3 radioisotope thermoelectric generators, which converted heat from the decay of plutonium into electricity. At launch, they produced around 800 watts, roughly enough to power a few household appliances. Even by the end of its mission, 2 decades later, they were still generating about 700 watts. Reliable, consistent, and robust. These power sources kept Cassini alive through the cold and darkness. Yet the use of radioactive material came with risks. NASA calculated that if Cassini had failed during its Earth flyby, the released plutonium could have led to an estimated 5,000 cancer-related deaths in a worst-case scenario. The probability of this was only 1 in a million, but the stakes were enormous. Ultimately, the risk was accepted, and the maneuver was executed flawlessly. Cassini swung past Earth, picking up the speed it needed and continuing on its trajectory into deep space. For nearly 7 years, Cassini sailed through the emptiness, with engineers on Earth carefully monitoring its course and health. There were no pit stops, no course corrections without reason. Every movement was part of a long orchestrated plan. And then, on the 1st of July in the year 2004, after more than 2.5 billion kilometers traveled, Cassini finally arrived at Saturn. It fired its engines, slowed itself into orbit, and became the first spacecraft ever to settle into a long-term mission around the ringed giant. The arrival itself was breathtaking. As it passed through a gap in Saturn's rings, Cassini took images that left scientists speechless. The rings were brighter, sharper, and more delicate than anyone had imagined. From that moment forward, Cassini was no longer just a traveler. It had reached its destination. The years of patient planning, the planetary flybys, the intricate math, all of it had worked. The doors to Saturn's realm were open, and this, as we would soon find out, was only the beginning. The Cassini spacecraft was not just built, it was crafted. Every nut, bolt, wire, and antenna served a purpose. Weighing in at over 5.5 metric tons at launch, Cassini was among the largest and most complex interplanetary spacecraft ever constructed. It stood over 6.5 meters tall, roughly the size of a 2-story building, and carried a payload of high-tech instruments built to endure the harshest environments known to science. This was not a simple probe. It was a flying laboratory designed to operate far from Earth in the icy realm of Saturn. To understand Cassini's capabilities, one must look at its core structure. At the heart of the spacecraft was a central body shaped like a box, housing computers, storage units, gyroscopes, and avionics. Mounted around this body were its scientific instruments, cameras, spectrometers, magnetometers, and antennas. Cassini carried 12 main instruments and several subsystems, each carefully shielded to survive exposure to intense radiation, low temperatures, and the vacuum of space. Every device had to last for years, far from repair. Power was perhaps the most critical challenge. At Saturn's distance from the Sun, sunlight is about 1% as strong as it is on Earth. Solar panels would have been impractically large and ineffective. Instead, Cassini used 3 radioisotope thermoelectric generators. These devices produced electricity by converting heat from the natural radioactive decay of plutonium into energy. Though only generating about 700 to 800 watts at full strength, it was enough to run all systems. Quiet, durable, and reliable. Perfect for deep space. Communications were handled through a large high-gain antenna, more than 4 meters across. With this, Cassini could send signals back to Earth, even when Saturn was on the far side of the Sun. Data speeds were slow by modern standards, but what Cassini lacked in bandwidth, it made up for in precision and endurance. Every bit of information, images, magnetic readings, gravity data, was stored, compressed, and transmitted across the void of space to waiting scientists on Earth. It was like whispering across 1 billion kilometers. One of the most fascinating aspects of the spacecraft was its propulsion system. Cassini carried hundreds of kilograms of propellant, not to speed up, but mostly to slow down, turn, and make subtle adjustments to its orbit. It used a main engine for major maneuvers, along with small thrusters for attitude control. Without these, it would have never been able to thread the gaps between Saturn's rings or perform the dozens of flybys that defined its mission. Precision in navigation was not a luxury. It was survival. And then, there was Huygens, the companion probe designed by the European Space Agency. Attached to Cassini like a seed pod, Huygens was built to detach and plunge into the thick orange clouds of Saturn's largest moon, Titan. While Cassini orbited above, Huygens would make history below. The design of Cassini had to ensure this transition would go smoothly. Accurate release, flawless communications, and timing down to the second. The integration of 2 separate spacecraft into one system was a feat of international engineering. Cassini's technology may now feel older compared to modern smartphones or satellites, but its durability, reliability, and brilliance remain unmatched. It was built in the era of compact discs and early cell phones, yet it operated flawlessly for nearly 20 years in deep space. That is a testament to the engineers and scientists who dared to build something that would work not for days or weeks, but for decades, millions of kilometers from home. Cassini was not just a machine, it was a masterpiece of ingenuity. The Cassini-Huygens mission was never meant to be a quick visit. From the beginning, it was designed as a deep, sustained study of the Saturnian system, something no spacecraft had done before. Its goals were bold and ambitious: to uncover the nature of Saturn's atmosphere, to explore its rings, to investigate its magnetic field, and to probe the mysteries of its diverse and intriguing moons. Each of these objectives was chosen because Saturn, majestic and distant, held secrets that could reshape how we understand the solar system. One of the central goals was to study Saturn's atmosphere in fine detail. The planet is a gas giant with no solid surface and a dynamic weather system that includes storms, high-speed winds, and changes across its seasons. Cassini was equipped to measure temperature, composition, pressure, and motion, using instruments that could detect everything from ultraviolet radiation to infrared heat signatures. By doing this, scientists hoped to unlock clues about how such massive planets form and behave over time. Another key objective was Saturn's rings, perhaps its most iconic feature. These rings are made of countless particles of ice and rock, ranging in size from tiny grains to mountain-sized chunks. Cassini aimed to study the structure, formation, and evolution of the rings. Were they ancient relics from the early solar system, or were they born more recently from shattered moons? Cassini mapped the density waves, measured particle composition, and watched how the rings responded to Saturn's gravity and magnetic field. Saturn's magnetosphere, the magnetic bubble that surrounds the planet, was also a major focus. Unlike Earth's relatively stable magnetic field, Saturn's is vast, dynamic, and surprisingly symmetrical. Cassini carried a magnetometer that allowed it to chart the shape and behavior of this field, especially how it interacted with the rings and the solar wind. Understanding Saturn's magnetosphere was not just about Saturn. It offered insights into how magnetic environments work across the cosmos, including around distant exoplanets. Perhaps the most exciting part of the mission was its dedication to Saturn's moons. Cassini was tasked with exploring as many of these moons as possible, from small, irregular chunks to major worlds like Titan and Enceladus. These moons are not mere rocks orbiting a planet. They are dynamic, active, and potentially habitable. Cassini revealed geysers erupting from the surface of Enceladus and clouds of methane on Titan. Each moon was a world unto itself, waiting to be studied, mapped, and understood. Titan, in particular, received special attention. It is Saturn's largest moon, and the only one in the solar system with a thick atmosphere. Because of this, Cassini was equipped with radar to see through Titan's haze, while the Huygens lander was specifically designed to descend to its surface. The mission's objective was to study Titan's weather, geology, and possible lakes or seas made of liquid hydrocarbons. Titan was not just a moon. It was a place where prebiotic chemistry might be unfolding even now. In essence, the Cassini-Huygens mission was a full-system exploration, aiming to understand the Saturnian neighborhood in all its complexity. It was not about collecting a few snapshots. It was about staying long enough to watch seasons shift, storms grow and fade, and moons move in their quiet, rhythmic orbits. Each objective was tied to a larger question. How do planetary systems work? How did our solar system form? And could life, in some form, exist in places we never thought to look? Among all of Cassini's remarkable achievements, one moment stands out as a defining leap for planetary science: the descent of the Huygens probe onto Titan. Titan, Saturn's largest moon, had long intrigued scientists. Shrouded in thick orange clouds and cloaked in mystery, it was the only moon in the solar system known to have a dense atmosphere. For decades, we had seen it only as a blurry sphere. But in January of the year 2005, Huygens would change that forever. Huygens was not built by NASA, but by the European Space Agency. It was a compact, dish-shaped lander, about 1.5 meters wide and weighing around 300 kilograms. For more than 7 years, it had remained dormant, quietly attached to the side of the Cassini spacecraft as it journeyed across the solar system. But when Cassini entered orbit around Saturn, the moment arrived. On Christmas Day of the year 2004, Huygens was released, left to drift alone for 22 days toward the distant world of Titan. The lander's systems were completely shut down during this drifting phase, except for a small timer designed to awaken it 15 minutes before it entered Titan's atmosphere. That timing had to be perfect. When Huygens finally woke, it found itself plunging into an alien sky, through a haze of methane and nitrogen, toward a surface no one had ever seen. It deployed a series of parachutes and began a 2.5-hour descent, sending back data the entire way. For the first time in history, we were receiving readings from inside the atmosphere of another moon. Huygens measured pressure, temperature, wind speed, and the composition of Titan's air. It recorded methane clouds drifting in the upper layers and detected organic compounds that hinted at complex chemistry. Cameras on board captured the dim sunlight filtering through the haze and revealed a strange, rust-colored landscape below. What scientists saw shocked them: river channels, drainage patterns, and a terrain shaped by erosion. Titan, it seemed, had been sculpted by liquid, not water, but methane and ethane. The original expectation was that Huygens would land in a lake, so it was designed to float if needed. But instead, it touched down on solid ground, possibly the dried bed of a methane sea. The surface was a mix of frozen pebbles and soft material, perhaps a crust above a more pliable layer. Remarkably, Huygens survived well beyond its expected life, continuing to transmit for over an hour after landing. It became the first and only spacecraft to land on a world in the outer solar system, and its legacy endures. The data Huygens collected opened an entirely new window into Titan's geology and atmosphere. Scientists realized Titan had a methane cycle similar to Earth's water cycle, complete with clouds, rain, rivers, and lakes. Yet the temperatures were unimaginably cold, close to -180 degrees Celsius. Despite this, Titan was active, dynamic, and surprisingly Earth-like in its behavior. Some began to wonder, if chemistry can be this rich in such a harsh place, could something more be happening beneath the surface? Huygens did not have the tools to answer that question. Its mission was short and focused, an atmospheric dive and landing. But it proved one thing beyond doubt. Titan was not a frozen, lifeless rock. It was a complex world with active weather and surface processes, and it deserved further exploration. Thanks to Cassini and Huygens, Titan transformed from a blurry orange dot into one of the most intriguing and promising places in the entire solar system. Cassini was not just a scientific workhorse, it was also a master artist. Over the course of its 13 years orbiting Saturn, it captured some of the most breathtaking images ever taken in space. Through the lens of its powerful cameras, we were given a front-row seat to the beauty of Saturn's world, a place of shimmering rings, icy moons, and strange shadows. These were not computer simulations or CGI renderings. They were real photographs, processed with care and precision, revealing scenes that looked almost too perfect to be true. From its very first images near Saturn, Cassini delivered wonders. The spacecraft showed us the rings in unprecedented clarity, sharp, clean arcs of ice particles stretching for hundreds of thousands of kilometers. In some photos, the planet's own shadow could be seen sweeping across the rings, creating deep contrasts between light and darkness. Other shots reveal details as small as a few hundred meters across, including delicate ringlets, mysterious gaps, and the complex patterns caused by gravitational waves. But Cassini's camera did not just look at the rings. It turned its gaze toward the many moons of Saturn, each one unique, each with its own story to tell. It flew past icy Enceladus, capturing geysers of water erupting into space. It imaged Pan and Atlas, strange moons with equatorial ridges that made them look like flying saucers. It showed us the battered surface of Mimas, scarred by an ancient impact crater that gave it the nickname Death Star Moon. Through it all, Cassini revealed a system as diverse as it was beautiful. Some of the most awe-inspiring photos came from Cassini's encounters with Titan. Though cloaked in haze, the moon's surface could be seen using infrared imaging, revealing vast lakes, mountains, and dune fields. In the soft light of Saturn's distant sun, Titan took on an otherworldly glow, a reminder that even in the cold outer reaches of the solar system, alien beauty thrives. Cassini's radar images traced the outlines of methane seas, and its cameras captured sunlight glinting off Titan's surface, a moment once thought impossible. Cassini also gave us stunning views of Saturn itself. One unforgettable image showed the planet backlit by the sun, with the rings shining like a halo and a tiny speck, Earth, visible in the distance. That image, known as "The Day the Earth Smiled," became iconic. Another photograph revealed Saturn's mysterious hexagon at the North Pole, a perfect six-sided storm larger than Earth. Cassini watched the hexagon shift with the seasons, its colors changing from blue to gold as Saturn's long year unfolded. Beyond the science and the data, Cassini's images stirred something deeper. They invited us to feel awe, to wonder at the scale and elegance of nature. They reminded us that space is not empty or dull, but alive with form, structure, and light. Each picture was a message from a faraway place, a frozen moment captured by a silent traveler. And although Cassini is now gone, the images it left behind continue to inspire a sense of connection to a cosmos much grander than ourselves. As Cassini's fuel reserves neared their end, the mission team faced a difficult but thrilling decision. With no way to continue long-term orbit corrections, they chose to spend Cassini's final months in the boldest way possible. Rather than drifting away quietly, the spacecraft would dive again and again into the narrow gap between Saturn and its innermost rings. These daring maneuvers, known as the grand finale, would bring Cassini closer to Saturn than any spacecraft had ever dared. It was a final act of bravery, an aerial ballet at the edge of destruction. Beginning in late November of the year 2016, Cassini performed a series of 20 ring-grazing orbits. It flew high above Saturn's North Pole before plunging down just outside the F ring, which marks the outer edge of the planet's main ring system. These sweeping passes allowed Cassini to capture images and data at resolutions never before achieved. From there, the spacecraft transitioned to an even more dangerous phase, diving between the inner edge of the rings and the cloud tops of Saturn itself. This region, only about 2,000 kilometers wide, had never been explored. Mission planners were uncertain what Cassini would encounter. Would there be ring particles dense enough to damage the spacecraft? Would the planet's upper atmosphere interfere with its navigation? The risks were high, but so were the rewards. Cassini would use its instruments to sample Saturn's magnetic field, gravity, and ionosphere directly. For the first time, scientists would be able to probe the unseen dynamics of Saturn's interior. With each successive orbit, Cassini swooped closer to the planet. It skimmed the top of the atmosphere and threaded its way between invisible bands of ice and dust. These maneuvers were more than just dramatic. They were scientifically priceless. Cassini mapped the mass of the rings with new precision, helping to determine their age. It measured how particles from the rings spiral into the atmosphere, a process that will one day erase them entirely. and it sent back stunning images of cloud structures and ring edges from just a few thousand kilometers away. The grand finale was not just about what Cassini saw, it was about what it felt. Instruments on board recorded changes in plasma, pressure, temperature, and radiation. The spacecraft was not merely an observer anymore. It was inside the very environment it had studied from afar for over a decade. Each orbit pushed the boundaries of engineering and navigation. Each loop was a dance on the edge of Saturn's gravitational well, and each pass was one step closer to the inevitable end. These final dives were Cassini at its most courageous. It had given us years of discoveries, and now it would offer one last gift. Data from the heart of the Saturn system, captured in real time as the spacecraft spiraled inward. The grand finale was both a swan song and a celebration. It was the most dangerous, most intimate chapter of the mission. And it proved, once more, that Cassini was not just built to endure, it was built to explore, all the way to the final breath. As Cassini approached the final days of its mission, it continued to do what it had always done best: observe. Even with its end in sight, the spacecraft captured images that remain among the most poignant in the history of space exploration. These were not just photographs, they were farewells. In the week before its plunge into Saturn, Cassini turned its cameras toward the planet, its rings, and its moons one last time, documenting the world it had come to know with a kind of reverence. One of its final time-lapse sequences showed Enceladus and its geysers of water vapor, backlit by the distant sun, still erupting into the vacuum of space. It captured the fading curves of the rings, Saturn's shadow stretching across them, and the planet's golden clouds glowing softly in the twilight. In these moments, Cassini was not just gathering data, it was savoring the view. From its vantage point near the edge of Saturn's atmosphere, it recorded everything it could before silence would come. The very last image Cassini ever took was of the place it would soon enter, Saturn's atmosphere. The shot showed the night side of the planet, dimly illuminated by sunlight reflected off the rings. It was not a dramatic vista, but a quiet, almost intimate farewell. No final burst of color, no grand explosion, just a serene view of the planet that had captured Cassini's lens and our imaginations for more than a decade. In its final snapshots, Cassini reminded us that beauty and wonder endure, even in the final moments of a long and noble journey. Cassini's final moments were not the result of failure or accident. They were planned, intentional, and poetic. With its propellant nearly exhausted, the spacecraft could no longer steer itself safely. Rather than risk contaminating Saturn's moons, especially those that might harbor life like Enceladus or Titan, NASA made a bold choice: to send Cassini into Saturn itself. It was not just a scientific decision, but an ethical one, to leave no trace where life might one day be found. The mission would end not with silence, but with one last dive into the planet, it had spent years studying. On the 15th of September, in the year 2017, Cassini began its final descent. Traveling at over 120,000 kilometers per hour, the spacecraft entered Saturn's upper atmosphere. Thrusters fired to keep the high-gain antenna pointed at Earth for as long as possible, allowing data to be streamed in real time. Cassini was not designed to survive this plunge. It would be torn apart by heat and pressure. But in those final seconds, it gathered critical information, measuring atmospheric composition, pressure, and magnetic fields from inside the very place it had orbited for so long. At a certain point, the atmosphere overwhelmed the thrusters. Cassini lost control and began to tumble. Its signal, once so steady, began to waver. Then, just like that, it vanished. The final transmission took over an hour to reach Earth, and when it did, a quiet pause echoed across the mission control room. Cassini had completed its journey. It had done everything it was asked to do, and more. What had begun as a complex machine now stood as a symbol of humanity's thirst for knowledge and our willingness to reach into the unknown. The data Cassini sent in those last moments was priceless. Never before had we been able to sample the atmosphere of Saturn directly. And thanks to Cassini, scientists could begin to answer questions about how Saturn's atmosphere interacts with its rings and magnetic field. Even in death, the spacecraft was teaching us. Its final breath was not a farewell. It was a gift, delivered through fire and gravity. A last transmission from the edge of science. Cassini's end was dramatic, but it was also deeply moving. The people who had worked on the mission for decades watched their spacecraft fall into the world it had come to know better than any human probe ever had. Some wept, some cheered, all stood in awe. There was sadness, but no regret. The spacecraft had not failed. It had fulfilled its purpose. It had ventured farther, lasted longer, and revealed more than anyone had dared hope when it first launched into the night sky 20 years earlier. Cassini's glorious death is now part of its legend. It did not fade quietly into the void. It faced its end with intention, courage, and purpose, and in doing so, it left behind not just data, but a legacy. One that reminds us that in the vastness of space, even machines can tell a story worth remembering. Even after 2 decades of exploration, Cassini's journey did not end with answers alone. In fact, some of the most important results were questions, strange, beautiful, and baffling questions. For every mystery solved, another emerged. Saturn, despite its elegance, remains a world that defies full understanding. Cassini peeled back the clouds, but what it found beneath them only deepened the sense that this gas giant is not as simple as it seems. Take the hexagon, for example. At Saturn's North Pole lies a 6-sided jet stream, wider than Earth, that rotates with astonishing precision. Its edges are sharp, its shape stable. For years, scientists have tried to recreate this phenomenon in laboratory simulations. While similar patterns can be produced under specific conditions, none explain how such a vast structure can remain so fixed over time. Why does it not drift with Saturn's powerful winds? Why is there no hexagon at the South Pole? And then there is the magnetic field, one of Saturn's strangest features. Most planets have magnetic poles that are tilted in relation to their axis of rotation. But Saturn's magnetic field is nearly perfectly aligned with its spin axis, something that dynamo theory says should not be possible. A magnetic field needs asymmetry to survive. And yet, Saturn's field is strong, stable, and symmetric. It should not work, but it does. Cassini measured it again and again. The data was clear, but the explanation remains elusive. Even the length of a Saturnian day has been hard to pin down. Gas giants have no solid surfaces, so you cannot track a landmark to measure one full rotation. Scientists tried using magnetic field variations as a proxy, as they had done with Jupiter. But Saturn's aligned magnetic field offers no such clues. Radio emissions, once thought to help, varied over time. Eventually, Cassini's data revealed that gravitational ripples in the rings could be used to measure Saturn's rotation with more accuracy, finally suggesting a day lasts about 10 hours and 33 minutes. But even this value has room for doubt. Other puzzles lie in Saturn's energy. The planet radiates more heat than it receives from the Sun, which is expected for young gas giants. But Saturn is over 4 billion years old. Some heat may come from helium rain falling deeper into the interior, generating friction, but this process is not fully understood. Could some unknown interaction between the rings, atmosphere, or magnetosphere be responsible? Cassini hinted at these processes, but could not confirm them. The auroras of Saturn add another layer of confusion. Unlike those on Earth, which are driven by the solar wind, Saturn's auroras sometimes occur without any solar activity. They appear, shimmer, and pulse, as if controlled by some internal force, perhaps linked to Saturn's complex system of moons or its powerful magnetic field. Cassini observed these light shows with multiple instruments, but could not fully decode their behavior. Something hidden is driving them, and it remains a mystery. Even the origin of the rings themselves is unclear. Once thought to be ancient, Cassini's measurements suggest they may be surprisingly young, perhaps only 100 million years old. And yet, they are massive, composed of clean water ice that has not darkened with age. Could they have formed from a shattered moon? Or were they captured from a passing comet? If so, why are they so pristine? Cassini provided clues, but not certainty. Saturn's rings are also disappearing. Slowly, but surely, the particles are spiraling into the planet, pulled by gravity and guided by magnetic fields. This ring rain may one day erase the very feature that makes Saturn so iconic. Cassini helped measure the rate of this loss, but we still do not know how fast the process is or when it began. In another 100 million years, the rings may be gone. For us, living in this brief cosmic window, their existence feels like a gift. And perhaps that is the greatest mystery of all: timing. Cassini arrived at a moment when the planet's seasons, storms, and features were shifting in just the right way to be observed. Was it luck, or does Saturn cycle through changes more rapidly than we thought? The data continues to be studied. New papers are published each year, teasing out fresh patterns from the terabytes Cassini left behind. But one truth remains clear: Saturn is not finished surprising us. Cassini's legacy lives on in these unanswered questions. Its mission proved that exploration is not about solving everything. It is about discovering what we did not even know we needed to ask. The gaps in our knowledge are not failures. They are invitations. Saturn still holds its secrets close. And thanks to Cassini, we now know just enough to realize how much more there is to learn. For centuries, Saturn's rings were seen as decoration, a celestial flourish, beautiful but passive. Cassini proved otherwise. The rings are not just ornaments. They are active, dynamic, and deeply connected to Saturn itself. In fact, some of the greatest clues to the planet's secrets may be written directly into the rings. These vast bands of ice and dust are like seismographs, echoing the motions of the planet's interior. They respond to gravity, to magnetic pulses, and even to Saturn's subtle shudders. They may hold the answers hidden deep within the gas giant's core. One of the most brilliant discoveries made during Cassini's grand finale was that the rings act like a giant stethoscope. As Saturn pulses and rotates, it sends out waves that travel through its gravitational field. These waves ripple through the rings, creating density patterns, gaps, and waves that are visible to our instruments. By studying the location and spacing of these ripples, scientists were able to estimate the speed of Saturn's rotation, a task that had long evaded traditional techniques due to the planet's lack of a solid surface. These observations also revealed another mystery. The mass of the rings, as measured by Cassini's gravity data, was much lower than expected. This suggests that the rings may not be ancient leftovers from the formation of the solar system. Instead, they might be young, perhaps no more than 100 million years old. If true, that means they appeared long after the planet itself formed. Could they be the remains of a moon shattered by a collision? Or the captured remnants of a wandering comet? The origin story remains open. And as stunning as the rings are, they are also fading. Cassini measured particles from the rings falling into Saturn's atmosphere, a process called ring rain. Over time, this slow but steady loss will erase the rings completely. In cosmic terms, this means we are living in a rare moment. The grand arcs of Saturn's rings may last only a few 100 million years, a blink compared to the age of the planet. Future civilizations, or future species, might look at Saturn and see only clouds, never knowing what once circled the planet. This transience makes the rings even more meaningful. They are not permanent features etched into the heavens. They are fleeting, fragile, and possibly accidental. And yet, they serve a powerful scientific role. They amplify the effects of Saturn's gravitational field. They act as sensors for changes in the planet's magnetosphere. They trace the paths of tiny moons, revealing the balance of forces that keeps this complex system in motion. Saturn's rings are not static. They are alive with motion and information. There is something deeply poetic about this. The most iconic symbol of Saturn may be the least enduring, and yet it may also be the key to understanding the planet's inner structure. The interaction between the rings and the planet is not just visual, it is physical. Rings migrate, particles collide, moons shepherd their paths. These constant interactions create patterns that, when observed carefully, reveal the workings of an entire planetary system. The rings are a window not only to Saturn's past, but to its inner workings. Scientists now believe that the rings might help explain not just Saturn's rotation, but the hidden shape of its core. Unlike the rocky interior of Earth, Saturn's core may be diffuse and fuzzy, blending gradually into the surrounding gas layers. The gravitational tugs from this uncertain boundary ripple out into the rings, where Cassini's instruments could detect them. From the rings, we read the pulse of the planet. They translate invisible forces into patterns we can see and study. In the end, the rings of Saturn are more than a mystery. They are a message encoded in ice and motion, waiting to be understood. They tell us that beauty and science are not opposites, that even the most graceful features of a planet can also be the most revealing. Cassini gave us the tools to begin decoding this message, and though the spacecraft is gone, the data it returned continues to whisper secrets from one of the most elegant planets in the solar system. Cassini's mission may have ended in fire, but its legacy burns brighter than ever. Long after the spacecraft was gone, the data it collected continues to shape our understanding of Saturn, its moons, and the broader mechanics of planetary systems. Scientists are still publishing discoveries based on Cassini's treasure trove of information, new theories about planetary formation, complex weather systems, and even the possibilities for life in alien oceans. Cassini was not just a mission, it was a foundation on which future exploration will stand. It is difficult to overstate what Cassini gave us. It was a mission of firsts, the first spacecraft to orbit Saturn long-term, the first to send a lander to Titan, the first to dive between Saturn and its rings. Its instruments revealed a system of exquisite complexity, moon after moon, each with its own character and mystery. It changed the way we look at gas giants. It changed how we define habitability. Cassini showed us that the outer solar system is not a frozen desert. It is alive, dynamic, and rich with scientific possibility. Cassini also raised the bar for international cooperation. A partnership between NASA, the European Space Agency, and the Italian Space Agency. The mission demonstrated what could be achieved when nations come together for a shared scientific vision. Thousands of people from dozens of countries worked on Cassini. Engineers, astronomers, students, and artists all contributed in different ways. It was a global achievement and a testament to human curiosity, imagination, and precision. As we look to the future, Cassini has already inspired what comes next. In the year 2027, NASA plans to launch the Dragonfly mission to Titan. This ambitious rotorcraft will fly from place to place across Titan's surface, investigating its chemistry, geology, and potential for life. Without Cassini and Huygens, Dragonfly would not exist. The new mission stands directly on the shoulders of what was learned from those who came before. It is proof that exploration is a relay, not a race, but a handoff from one generation to the next. There is still much to explore. Enceladus remains a prime candidate for life beyond Earth, with its subsurface ocean and active geysers. Saturn's atmosphere holds secrets about planetary physics that we have only begun to understand. And the rings, those haunting, beautiful rings, are fading, but still whispering clues about the formation and evolution of worlds. The Cassini mission was never meant to answer everything. Its true gift is that it taught us how to ask better questions. Cassini's legacy is not just in the data it left behind, but in the sense of wonder it reignited. It reminded the world that space exploration is not a luxury. It is a path to understanding who we are, where we come from, and what else might be out there. Cassini took us to the edge of Saturn, and in doing so, pushed the boundaries of human knowledge. Its story is not over. It lives on in every future mission, every scientist it inspired, and every eye that looks up at the night sky and wonders. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.